All right, let's get started. Good morning. How's everyone doing? Is this better? No, that was better. Bad. All right, welcome back. So, start with any questions anyone has? Questions about the course or questions about the world in general? No? All right. Okay. So, let's get started. So, the objective for today is we are going to understand the candidate elimination algorithm, and we are going to sort of go through an example quickly. The algorithm is just a bunch of steps, so I won't spend too much time on it. We will go through the example to see how it really works. There will be a couple of questions in this times gradients that asks you to do that as well. So you will get a good practice of how to do that. Then we are going to hopefully move to the next part. Okay. I think so far we have been a little slow, but that's okay. We can catch up. There are a couple of topics that I always keep I can skip them if we don't have enough time. All right, so if there are no questions, let me get started with what we want to do today. All right, so last time we were looking at this relationship of more general. This won't stay back. Okay, so that's fine. Oh, I'll just move this thing. All right. So more general or equal to relationship. So we were looking at hypotheses, right? So the idea was that if you have two hypotheses, you can compare them. You can figure out if one is more general than other, and we had an exact definition. So if you have a hypothesis H and you have another hypothesis J, right, or G. So you can say that G is more general. So this is just a way of writing that relationship. So G is more general or equal to. So it's maybe as general as H or more general if. So the condition is this will be true if whatever H labels as malignant or as belongs to the class, G will also label them as belongs to the class, right? It's pretty easy. So if H of X for any X, right? For all X belonging to our data set D, right? If H of X is equal to true or malignant, it implies that G of X will also be true. So that is the notion of general, right? So whatever H considers as malignant, G will also consider as malignant. G might also consider more things as malignant as well, but it's not necessary that H will consider them as well. So just sort of a illustration, let's say this is all of our data, okay? So let's say this is our data set D, and we are talking about the training data set, of course. Then let's say that all the X's in this section, right? So these are everything that H calls malignant. Then if G is more general than H, it means that G will consider all of these as malignant as well as some of these, some extra. All right, a little more than that. So that's the idea. If there is equality, that means that both of their sets will coincide exactly. So is that clear? And then you can also look at it in a different way. It also means that if G of X, so for any X, if G of X is equal to false or if benign or does not belong to the concept, it implies that H of X will also be benign. Right? Because the idea is that, remember, the X that G considers as benign will be all over here, right? And since H of X is over here anyway, the one that it considers malignant, it will never call something malignant if G does not call it malignant. So it's just two ways of understanding the same thing. Any questions about that? All right, and now we can also look at the more specific, the other way around. So let's say there's another pair of hypotheses. There is H and there's S, okay? And if we say that H is more general than S. So I just flipped it around. What does that mean? So if H is more, it just sort of is other way around, which means that if S of X is true, implies that H of X will also be true. So it's that's the notion of more specific or less general, right? So the idea is that if H is more general than S, that means that H will label more objects malignant than S, and everything that S labels as malignant will be inside that set, right? So remember that the notion of general and specific comes from how many objects do you consider malignant. So something is very specific if it only considers a very few objects as malignant, and something is very general if it considers everything or labels everything as malignant. So that is the idea, right? So with that, we were looking at one theorem, the version representation theorem, right? So the idea behind this theorem was that if you have the version space, which is the set of all hypotheses which are currently consistent with your training data set, right? So you have your version space VS, then you can order all of the hypotheses in this version space based on how specific or how general they are. So you can have some very specific hypotheses over here, so you could order them all, right? And what happens is that there will be some hypotheses such that you cannot make it any more specific. You cannot have any more specific hypothesis than that. So you could have some hypothesis S, you will have one at least, such that you cannot go any more specific than that. If you go more specific, then you will not be inconsistent with your data anymore, right? So all those hypotheses which will be of that type, we call them maximally specific hypotheses, and that set, an uppercase S, is called our most specific boundary. And the same thing is true on the other side. There will always be at least one hypothesis such that you cannot be more general than that. If you make it any more general, which means that if you accept any more objects as malignant, then you will become inconsistent with your data set, right? So with your training data. So we call that set as uppercase G. We call it most general boundary. And that will be true for any version space, right? You can order them in that way. So you can have multiple here as well. Okay. So what version representation theorem says is that if I take any hypothesis H over here, then there will always be one hypothesis G and one hypothesis S in uppercase G and S, such that you can kind of form this relationship. So the idea will be that G, of course, will be more general than H. It has to be, because this is the most general hypothesis. And H will be more specific than S. So you will always find two hypotheses on these boundaries which will bound your H, right? And the reason we have that is because of this theorem, it turns out that we will not really need to learn H at all. We can just learn the boundaries, and that will be enough. And that is the sort of the beauty of candidate elimination algorithm, is that it only goes with learning G and S, and that is why it is more efficient than the other one that we saw, the list and eliminate, which kind of looks at the entire version space at all times, right? So that is the idea, and the proof is actually fairly straightforward. So what we need to prove is that we need to prove two things. We need to prove that what we need to prove is that if H belongs to version space, then there exists G in uppercase G and S in uppercase S, such that this relationship holds. Okay? And So that is one side of the thing. So part one. And the part two that we want to prove is the other way, which is that if there exists if there is a hypothesis such that G is, they're bounded by this, implies that H will belong to Virgin space. All right, so we want to, what this theorem says is that both sides will be true. And it's kind of easy to do that. If you look at the handouts, there is a little more detailed proof of why. I will sort of give you a few hints. Proofs are not the main part of this course, so I don't really go into proofs that much, but I do have the proofs, at least sketch of the proof in the handout, so you can look at it. But let's just go with it just for a little bit, right? So let's look at this, right? What this says is that if H is in the Virgin space, then there will be at least one hypothesis which is in G and one in S, such that that thing is satisfied, right? And the way to sort of understand that is that if H is in the Virgin space, that means H is consistent with the training data, right? And if H is consistent with the training data, then there could be three things. One is that H might be in S itself, that means it's the most specific, then this condition is true, or H might be in G. But if H is inside, let's say H is not in G or H is not in S, then you will have something, you can always make it a little more general, right? Because H is consistent with your training data. That means there are all the malignant tumors are classified as malignant by this particular example, right? Which means that if I make my H a little more general, it will still be consistent with my training data, right? And that more general would be in my G. So that's sort of the basic idea. And then you can also look at this other side as well, which is that if H belongs to the Virgin space, right, then you will have something on the either sides which will bound it. So that proof you do more by contradiction. So let me just bring up the proof here. All right, so let me switch to this. So these are the handouts that go with all the slides. I don't know if you have seen it, but on the website, you'll have the slides and you have the handouts. The handouts have similar stuff to the slides, but a lot of times I have detailed proofs within that as well. Slides only have what we see, right? So if you look at this, I'm just showing it so that you can go back and look at it. There is a proof there that you can go through, and it's fairly easy to understand. Right? So essentially what you do is you say that if you want to prove one side, right? So the one side is that let's assume that belongs to a hypothesis space, and let's say it is bounded by G and S, right? But we don't know yet that it is part of the Virgin space. So we have to prove that it will be a part of the Virgin space. So the way to understand that is that, let's go back. Is that let there be some H, right? Some H that belongs to the hypothesis space. And we assume that there is so we are trying to prove this one. So there is some G that belongs to G and S that belongs to S, and they bound the whole thing, right? What does this mean? What this means is that now, of course, these two are in the Virgin space, they are in the boundaries, right? So let us sort of try to do it by contradiction. So let us assume that H is not part of the Virgin space. So if H is not part of the Virgin space, it means that H misclassifies some objects, right? There might be some object, some X, such that even though X is malignant, H is calling it benign, right? But so let X be such that the actual concept calls it malignant. but h of x is benign. So what we are trying to do it by contradiction, which means assume h is not part of the version space, right? So what does this mean? It means that h is calling something benign even though it is malignant, right? So let's look at S. Now since h is more general than S, right? Which means, so if you remember when we were talking about how to relate these two, right? So whatever h calls as benign over here, whatever h will call benign, if h is more specific than S, then S will also call it benign, right? That was our relationship. It means so be benign because S is more specific than H, right? Which means that S is making a mistake on X. But that could not be true because that's a contradiction, because S belongs to the version space, right? So S belongs to the version space, that means cannot make a mistake. However, if H is making a mistake and H is more general than S, then it means that S is also going to make a mistake. So these are sort of, I think if you sit down with this proof and just go through it line by line, it will be very clear. It's fairly easy to understand. The idea is just to look at what does it mean if one thing is more specific than other. So you can quickly arrive at these contradictions and get the proof. All right. So I won't spend too much time on this. All I want you to understand is that because of this theorem, it turns out that it's enough to only learn the boundaries, the G and S, and that will be it. So if you know what is in G and what is in S for a given data set, you will know that for any H that is in between, that will be already bounded by some G and some S here. So you don't really need. All right. So that is the idea. Okay. So with that in mind, let's look at the candidate elimination algorithm. Okay, so this is how the algorithm works. Okay, so let me just give you a general feel of this. So what it does is it starts. So the idea is you are given some training data set, right? So you are given data set in which every object or every training example will be the data object X and its true label, of course. That's your training data. You start with your boundaries as most specific and most general. So your initial S, the most specific boundary, contains the most specific hypothesis, which accepts nothing, right? It rejects everything. And on the other side, you have your most general hypothesis, right? So that makes sense because you haven't seen any data. So right now, your version space contains everything. But you can quickly see that you don't have to enumerate your version space. All you do is you just initialize it with your boundaries, right? And you can see that everything will be in between. So your representation theorem will still work. Now, once you get your first training example, based on what its true label is, right, you do one of the two things. So if your example is positive, or if it's a malignant tumor or belongs to the concept, the first thing you do is you check that your G is consistent. Now remember, at every step, you need to make sure that whatever your version space is, I mean your boundaries, they should be consistent with your training data. Otherwise, it won't be a version space anymore, right? So first thing you quickly do is that, is your G consistent with your training data? If it's not, then you remove the hypotheses which are not consistent, okay? Then, for positive examples, you basically try to fix your S. So think about this way, right? Right now you have the most specific hypothesis in your specific boundary, right? Now you have seen one training example, and you have seen that it is malignant. So now you are going to revise your notion of the most specific because you have seen something which is positive, right? That works very much like your find S algorithm. So the first training example you see, you say, okay, now I know what at least one positive example looks like. So now I cannot have this as my most specific boundary, right? Because this one rejects everything. But now you have seen one positive example, so you need to refine it. So what you do is you remove every current every current hypothesis in your uppercase S, the most specific hypothesis, and you remove it because that is definitely not going to be part of the version space anymore, and then you generalize it a little bit. So you do minimal generalization. You just go one step ahead, one step generalization, and I'll tell you what that means. And then you replace that with this, all right? And once you replace that, you also want to make sure that there is a corresponding boundary, a corresponding hypothesis in your most general boundary which connects the two, because you want to make sure that the theorem always holds. And then you remove any hypothesis that is, and then you all, this third step ensures that your uppercase S, the most specific boundary, contains only the most specific hypothesis. It has nothing that could be made more specific, all right? So that is the idea for a positive example. Negative example, you do the other way, right? So negative example means that now you have seen something which is benign or which does not belong to the concept, right? However, your current most general boundary right now accepts everything, right? But now you have seen at least one negative example. That means you need to fix it so that it is consistent with your training data. Steps are very similar here as well, okay? So when you do your gradients problems, you'll sort of go through step by step, so you'll understand what it means. And I'll go through an example here so that we understand it as well, all right? So let's go with an example. So here is our current state. This is my most specific, this is my most general. I get my first training data point over here. Okay, the first training data point is this. This is again that tumor example, and it's positive, all right? So the first thing that we do when we get a positive example is first we check if we need to fix our general hypothesis, right? Remember, the first step is remove any G from G for which Gx is not positive. Now clearly right now our G is accept everything, so it is going to call it positive. So this is fine, this stays as it is. But now what we do is we make this more specific, right? We fix this, right? And here we are assuming these are conjunctive concepts, remember? So the way to make them more specific is just to replace it, just do a pairwise and bring it here. So now this and this are the boundaries, right? And you can easily see that these both are still consistent with your training data, and you can be assured that any hypothesis which is within this boundary would also be consistent with the training data, because that's the theorem. But you can also sort of figure it out otherwise, right? Now let's say this is another example we get, and let's say this is also positive, right? So now what happens is that you again check your general boundary first, and this is still fine, right? This is going to accept it as positive. And then you try to make this more specific, because clearly this one is not going to agree with this one. This hypothesis is going to call this negative, right? Because it is disagreeing in this, the fourth feature, right? So now you make it a little more specific, but minimal specific, which means that you remove one of them, make it question mark. Now this hypothesis here is the most specific hypothesis which agrees with your training data so far, right? So now this becomes, and this is still the same. Then comes your next one, which is negative, right? Once negative example comes, everything becomes crazy. So when a negative example comes, of course, the first thing you want to check is that is your most specific boundary still consistent with this? And in this case, it is, right? Because this one is negative, and it sort of, even this one will call it negative, right? Because it disagrees with at least one of them, oval and circular. However, let's see this one. Now, of course, it is clear that this one is not consistent with your data anymore, right? Because this one calls everything positive, whereas this one is a negative example. So you want to generalize it. So how do you generalize a hypothesis, right? So with conjunctive hypothesis, the idea is that all of these are the minimal generalizations of this one, right? So G naught is all question marks. The way to generalize it would be replace any question mark with one of the values, right? And you can actually replace it with ci and not of ci or oval, right? So ci question mark question mark question mark everything, and oval and so on. But what you will quickly see is that a lot of them will not be consistent with your example, because if you remember in the steps here, you also you have to check every generalization, but you also have to figure out that they are consistent with your training data, right? So here what I did was, just to save some space, I just wrote the ones that are consistent with this training example. So circular definitely is going to call it negative, only large is same, and so on, right? Then next thing what we do is we figure out if any of these hypotheses have something in this more specific boundary which is more specific than this, right? Because that is what will ensure the version space theorem, right? So let's look at this one. So this is question mark, dark, question mark, right? If you see, this one is not more specific than this, because they are not agreeing in this one, in the dark or whatever that color feature. This is not more specific than this, because whatever this calls as positive is not the same as what this calls positive, right? So you remove it, that goes out, and this one also goes out, right? So these both go out, and these three stay. Now try to look at it a little more carefully. The beauty of this is that one step, the first step, ensures that whatever you're adding to your version space is consistent with your current training data, okay? But the second step that I did, like this one, right? This one is still consistent with your the current training data, but by looking at if it has a more specific thing here, it is ensuring that it is also consistent with your previously observed training examples. Because those examples, these ones, were the ones that had resulted in this specific boundary, right? So it's kind of like a memory of this algorithm. This algorithm has a memory in the sense that by this step over here, right? This step ensures that you are not only consistent with your current training data, but also consistent with what you had seen in the past. But you're not really looking at every training data that you had seen in the past. That would be too inefficient. But all you're doing is you're comparing it with what you have so far and ensuring that it's consistent with that, right? So that's sort of very interesting in a way, because that's how a lot of machine learning algorithms work. So as the training data comes in, you do not want to keep going back to the entire training data over and over again, right? Because that will be too inefficient, especially when you're talking about a large amount of training data. That is not a good idea. But what this algorithm does is that simply by ensuring that it is consistent with this one, it is making sure that you are still consistent with all of your training data, okay? And the only reason this works in this case is because it's a pretty simple setting, right? We are assuming there are no errors in the data and so on, right? So everything is very controlled. It's a very controlled environment, and that is why you can get this beautiful effect of sort of working with this data. All right, so let's keep going. Let's say we get one more example, which is positive. So just before that, so after seeing these three examples, this is our current most general boundary, and this is our most specific boundary. And then we get another positive example, which means that we need to first we need to fix our specific boundary. Oh, actually, first we need to make sure that what you get now, the new one, is consistent with the general boundary. So this one will go away, because this one calls circular things as positive, whereas we just saw a positive example with an oval shape, right? So you remove that, and then you make this more specific by sort of doing a pairwise AND with this, and then this is your boundary, all right? And that's how you sort of keep going. And the idea is that at some point, your two boundaries will coincide, and you will be left with one hypothesis, which will be your target concept. So if you're given enough data, you will come together, all right? But if you're not given enough data, for example, in this case, right? So this is where we stop. Even though you didn't get a concept, you still got a version space, which is consistent with your training data. And I'll show you later how to use that to make predictions. But this is one key difference from find S algorithm, what find S would do is it will give you one concept and say this is your target concept when it might not be, right? But what candidate elimination does is that it says that essentially what you're getting now is that it didn't get enough training data, so it could not arrive at the target concept. Okay. However, here is what I have so far. Right. That's a pretty more usable algorithm than something that gives you something and says it is correct when it is wrong. Right. So that is sort of one advantage of candidate elimination algorithm. Any questions so far? Yes. That is broadly the idea, but you still do some checks. So the question is that when you get a positive example, you work on specific boundary, and when you get a negative example, you work on the general boundary, and that is correct, right? Because that's what the algorithm says here. Step 2 in each one of them. However, you still want to make sure that your other sides are consistent with your data. So you have these checks first. So even for the positive case, the first thing you want to make sure is that your general boundary is also consistent. So that's what we did in this step. So remember, when we got this example, it's a positive example, right? So the first thing I do is I check that my general boundary, everything is consistent with this example. If not, I take it off. And then I start working on my specific boundary. But so in a way, you're right, but there are still some border cases that you want to take care of. Any other questions? Yes.
So we're only looking at the jump concept.
Right.
The specific boundary is always just going to have one hypothesis.
Yes. So the question is, will the specific boundary always have just one hypothesis? That's right. But for conjunctive concepts only. This algorithm actually can work for any type of concept class, even though the example here is for conjunctive concept. But if you look at the algorithm itself, right, all it says is it doesn't really make any assumptions about the hypothesis, the bias that we have, that it has to be a conjunctive concept or not. All it says is that there has to be some way of doing a minimal generalization or specialization. So if you have a way to do that, you can apply it to anything else. But for conjunctive concepts, this is the way to do it. And this boundary will always have one hypothesis, always. There are some, if you look at what should I say? If you make it a little more interesting, which means every feature can take 3 values instead of 2, then you will start seeing some interesting effects there. But then the notion of conjunctive becomes different as well, right? So yeah, I don't think we'll look at that at all. But for the conjunctive concept, that is true. Any other questions? Yes. Okay, so the question is for the third example, when we saw, so this was our state before we saw the third example. Third example came, this is negative, right? So the first thing we want to check is that, are you talking about a specific boundary, right? Yeah, so first thing we want to check is this any hypothesis in the specific boundary, is it still consistent with this one, right? So in this case, if you check, it is consistent, because this hypothesis is going to call this object as negative, right? Because it's a conjunction, right? It means that it will only call those objects positive which are circular, large, light, and thick. However, this one is oval, so it is going to call it negative, so it is fine. But you do want to make that check all the time. So one interesting property, of course, of candidate elimination is that it gives you the version space, which is nice, right? Another thing is that if there is an error in the training data, if for some reason something is flipped, the label is flipped, what will happen is that your boundaries will become empty. And I will not go through that example here, but you can do that test at home, which is that if you just take some target concept, okay, and then you say that I'm going to label some training data, and I, purposefully I switch a label of one, I introduce error, right? What will happen is that if you run through this example, it will as soon as it sees that that wrongly labeled example, everything will become empty. And you can sort of think about it why it will happen, because this algorithm works on that strong assumption that your data is correct and your concept is in this class. I mean, your concept is conjunctive, right? If those things are not true, it will become empty, and which is actually a good thing, because it is essentially a test for the data, right? So if it becomes empty, you know that there is something wrong with the training data, or the concept is not really conjunctive. So that's also another interesting property of this algorithm. All right, so that's sort of the how to understand this. You have boundaries that are far apart, and then as you get training data, you slowly sort of bring it together. If you have enough training data and your concept is conjunctive, or it belongs to the whatever class you have, it will converge. If it doesn't, you at least have a version space which is consistent with your training data. Now the other thing is, what do you do with that version space? So let's say your algorithm did not converge to one concept, right? To your target concept, which means, let's say this one, right? So this one is our version space. So can I still use it for predictions, right? Can I still use it to take a new object X star and call it malignant or benign? And the answer is that you can in some way. So let's look at that, right? So you can look at some cases. So what you do is, all you have in candidate elimination are your boundary sets. Here you have S and you have G. So one thing you can do is you can say, okay, is my X star consistent with every hypothesis in S, the most specific, right? If it is, right, it means that every hypothesis in S calls it, let's say, positive, okay? It would mean that any other hypothesis, which would be more general than this one, will also call it positive, right? Which means that you can easily say that X star is also positive. And same thing you can go in the other way, which is looking at G and going back, right? Oh, I think I flipped it. I flipped it. So you have some new X star, right? And your candidate elimination algorithm has given an S, which is your most specific, right? And G on the bottom, right? It has some things, it has something. So you can have multiple cases, right? One is that X star is called positive by all your most general hypotheses, right? If that is true, that means that all of your most general hypotheses considers this example as malignant, which means by Vergen's the representation theorem, you know that every hypothesis which is more specific than these ones will also call it positive, because that's the nature, right? So then you can easily say this is positive. However, on the other side, if it so happens that X star is called negative by all of your most specific examples, then you know that there will not be any hypothesis under that in your Vergen space which will call it positive, right? Because it's stopped at the most specific boundary. That's why we call them the boundaries. So you can, in principle, use these boundaries to make predictions on X star, okay? But it can so happen that some of the hypothesis calls it positive, some call it negative. Then you can't do anything. Then you say, I don't have enough information. Or you can maybe use stuff like, let's count how many hypotheses call it positive, how many call it negative, and choose the higher one. So there is no principled way to do it at that point, okay? So the point is that in some cases you can use the Vergen space to make predictions if your X star falls in one of these two cases. However, if it is mixed, like some hypotheses in G call it positive, some call it negative, and so on, then you do not have enough information. But again, the beauty of this is that at least you can make that claim, right? At least you can say, I do not have enough training data to say anything about this new example. All right, so that's sort of the general idea. Any questions so far? Yeah.
But in this case, under no circumstances will it, let's say, will it call a negative hypothesis positive? Will it do that?
The Vergen space?
Yes, I mean, you say like we have a specific
Right.
So suppose we have an example which is negative,
Uh-huh.
but will it mistakenly take this as positive or vice versa?
A new example, an unseen example. Yeah, it could. So, I mean, you can take a simple example of, just when this was your version space. Let's say you don't get any training data, the candidate elimination algorithm will output this as your version space, right? So now, if you get an X star, this one is going to this one is going to accept it, this one is going to reject it. So now you don't know what to do with this one, right? So and you can come up with examples even like here. Let's say this was your training data, so this is your version space, right? This, if you get another example, it could get mislabeled, right? Because this is going to accept it, this might get, any new example might get rejected with this one. So it's not necessary that it will always give you a clean answer. So that's I mean, it's unfortunate for this algorithm, but that's kind of true for any machine learning algorithm, that they are dependent on the data that they get for training, right? At least if your algorithm can say that I do not have enough data to make any judgments about this example, that's a good thing, all right? So that's yeah. I'll not look at this, but this is sort of some more examples. I think that going back to what you said is that there could be cases when a new example could get sort of mislabeled by some and like that. All right, and then this is how you use the partial version space. All right, so now let's quickly sort of end this whole discussion. So I told you one algorithm, candidate elimination, works very well for, at least for conjunctive things, it works pretty well. However, as I said, this could work well in any case, right, for any kind of concept. So now let's look at the notion of why we use, what happened when we use our target concept. And we talked about this earlier as well, right? Remember that if you do not make any assumptions about your concept space, then your concept space is 2 power 2 power d, right? Where d is the number of binary features that you have, very large space. However, if you make assumptions that our concept space is, so this is our 2 power 2 power d, and then I say, hey, I'm only going to assume that my C belongs, the target concept belongs to a conjunctive space, then we are only looking at 3 power d plus 1. So we have reduced it, right? But what happens if my C is not here? What if my C is here, right? Then, of course, as I showed you in candidate elimination, it would become empty. The version space will become empty. So at least you will know that your concept, the assumption that you started with is not true. But can we come up with an algorithm which can still learn this C, right? Even though it's not in the conjunctive space, which means that can we come up with an algorithm which does not make any assumptions about the concept, where does the concept lie, right? So that is sort of saying that we want to search in this whole space, right? So that's a very key assumption. So after a couple of weeks, we are going to look at topics like linear regression and logistic regression and so on. The idea there is, and some of you might be familiar with regression, right? The idea is that you have a bunch of points and you want to fit a line to that, right? So in that case, you're biased. You're saying that even though there could be any curve that could fit this set of points, I'm only going to learn a line, right? Which means I've significantly reduced my space of possible solution, right? I have made this bias. We call this the inductive bias, right? This reduction. I think I mentioned that earlier as well. So this reduction of this target space from 2 power 2 power d to 3 power d plus 1 is a form of inductive bias. Same way, from trying to learn all the curves, trying to learn only straight lines is another inductive bias, right? And we have already seen with all these algorithms is that by making this inductive bias, we have made our job very easy, right? Because now we are only looking at this space and we can come up with efficient algorithms and so on, right? But it turns out that if you do not make that assumption over here, Then to learn this C, right, with no inductive bias, okay, to learn C, we need 2 power d training examples. Oh, so we need 2 power d training examples. All right. So which means that if you want to learn a C without making any bias like this, any assumption like this, you will need the entire data set to do the training, which means that you're not learning at all, right? We call that rote learning, which is, you know, the label for everything that could happen. So when a new object comes, since it would also be in your training data set, all you do is you just see what its label and give it out, right? So that's rote learning. So the point that I'm trying to make is that if you do not make any inductive bias, then you cannot learn anything. All right, for machine learning algorithm, right? We're not talking about us learning. Well, even for us learning, right, we do make biases in our mind, right? For example, when we were kids, they used to make us learn these multiplicative tables, right? And they just make us learn what is 1 times 1 all the way to what is 10 times 1 and 10 times 10 and everything in between. So that, and we used to just learn it by rote. We never understood why is this happening. So that when we went on an exam and they asked us what is 9 times 4, we immediately looked in our memory and said 9 times 4 I saw was 36 and I put it there, right? However, another way to do this would be if somebody could tell us how this works, right? And just say that, you just need to do some multiplication or add it that many times or so on. And then when you get that problem in school, you do not know the answer. You do not know that training example in your mind, but you can work it out because you are making that bias that every multiplication is essentially a series of sums, right? So that is the idea. So even in machine learning, it's the same thing. And that is what we will see from now on, is that every algorithm is going to make some inductive bias. Okay, so when you look at any new machine learning algorithm from now on in the course or outside, the first thing you want to ask is, what is the bias it's making? What is the assumption that it is putting on your space, which is making it able to learn whatever it's trying to learn? Because if you do not make any assumption, you can be sure that on February 8th, I had told you that if you do not make any assumption, you will need the entire data set to learn anything meaningful. All right? So that is a very important point in machine learning. Any questions about that? All right. As always, we are still running very slow, but that's fine. This kind of ends our discussion on this part 2. So if you have any questions, we can certainly talk about it next time. Let me just quickly introduce what we're going to do next.